Alright, today we're going to cover the ideal gas law, which is still going to be a law, which is still an observable pattern in nature, but we're going to talk about it under ideal conditions. Now, for the ideal gas law, we're going to talk about the relationship between pressure, volume, temperature, and the number of moles of gas, or N. Okay? And that's the only thing. And instead of P1 and V1 like we've had with the other gas laws, this is just going to be one gas in one set of conditions. And it's really a combination of all the laws that we learned. It helps us approximate real gas behavior so that we can take some of these things into account because like we mentioned earlier, rarely do we hold all of these things, separate. Now the equation, and you got to write this into your notes, is going to be PV equals nRT. Okay, and here's what this stands for. The R is the ideal gas constant. Okay, right here. This is something that's given. It's kind of like Avogadro's number. We are going to mostly use this value right here, 0.08206. This will be given to you. Okay, there is another number for when pressure is in pascals, but we're not going to treat it that way. The thing is, if you look at these units, this tells you what units everything has to be in. So volume has to be in liters, pressure has to be in ATMs, okay, N is going to be moles, and T has to be in Kelvin. Okay, so you always want to make sure that you check the units before using the equation because they have to be in ATMs, liters, and Kelvin. Okay, that has to happen that way. All right, so let's do some samples. It says, what is the pressure? Okay, what is the pressure in ATM exerted by a 0.500 molar sample of nitrogen gas in a 10-liter container at 298 Kelvin? Okay, so let's go ahead and try to solve for this. Pressure is 0.5, no, sorry, that's not what we're doing. Let's try that again. Okay, refuel here. All right, we're looking for the pressure. All right, it says what is the pressure? Now I set you up because it says in ATMs, but we would know that if you ever find the pressure with the ideal gas law, it's always going to be in ATMs. The moles are N. N equals 0.500 moles. Okay, the volume, 10.0 liters. Temperature is 298 Kelvin. Okay, so we're going to have PV equals nRT, and go ahead and plug and chug. We're looking for pressure. You've got 10.0 liters is equal to 0.500 moles. Remember, we also have our ideal gas constant from before, which is 0.08206, and then we've got our temperature, which is 298. I'll show you how the units cancel out here in just a minute, but we got to do this math. So we're going to take 0.500, we multiply it by 0.08206, multiply it by 298. In order to get pressure by itself, we're going to go ahead and divide both sides by 10.0. Three significant figures, because that's what all of our data has, and our pressure is going to come out to be 1.22, and remember it's going to be ATMs. Okay, so there's one sample. All right, the next one, what is the volume in liters? So if we do our known and unknown, what is the volume? And for known, we have 0.250 moles. We have 20.0 degrees Celsius, which we're going to go ahead and take to 273 Kelvin. Okay, and then we also have a pressure value of 0.974 ATMs, and we want to know the volume. So we're going to go ahead and have PV, and everything is already in the correct units. Okay, it's in ATMs, it's in Kelvin. We're going to find volume in liters. Remember, if it was in something besides ATMs, you'd have to convert it first and then solve the rest of the problem. So PV equals nRT, and this time we're still looking for the volume. So I'm going to go ahead and manipulate it ahead of time, just to show you two different ways. So we were left with volume equals moles times the ideal gas constant times temperature over pressure. So I'm going to put the units in to show you how they all cancel out. 0.250 moles. Then you have your R value, which again is a given constant. People did a whole lot of math to figure out what this was going to look like. You've got liters times ATM over moles times Kelvin. So that's how the mole unit cancels out right there. And then our temperature value is 293 Kelvin. So there you lose the Kelvin unit. We're dividing that whole thing by the pressure. So divided by 0.974 ATM. So then we lose the ATMs and we're left with liter. So this is where our unit comes from. And it's going to be 6.18 liters. 3 significant figures. Okay, let's do one more. So this time it wants to know mass. Okay, so we want to know mass. Mass is always in grams unless it's specified differently. But we have volume of 10.0 liters. The temperature is 27 degrees Celsius or 300 Kelvin. Our pressure, 3.50 ATMs. Okay, now here's the thing. We don't have mass, but we do have moles. So we're going to find moles first, and then we're going to use molar mass to convert it. So PV equals nRT. All right, we're looking for moles right here. So let's plug it in first, and then we'll solve for it. So 3.50 for our pressure times 10.0 for our liters. We're looking for N, 0.08206 times 300. We got to get N by itself, so we got to divide both sides by 0.08206 and 300. So 0.08206, 300. Be careful when you do this math. You want to make sure you take 3.50 times 10, hit equals, take that, divide it by 0.08206 equals divided by 300. So make sure you're getting the math correct for the order of operations here. Alright, so our mass is going to be 1.42 moles, and it's chlorine. Now one of the things, if you remember about chlorine gas, chlorine is part of Hunkel Fibber, so we find it as Cl2. So the last step that we have to do, we've got 1.42 moles of chlorine gas, and we got to go to grams. So we go to the periodic table, we find out that chlorine's molar mass is 35.45. We need 2 of them. Let's put it like this. Most of the time we'll do this ahead of time, but you've got grams of chlorine, 1 mole of chlorine. Alright, and then we multiply that out with 3 significant figures. With rounding, we get 101 grams of chlorine. Okay, so that's the ideal gas constant. Hope that helps, and we'll do problems in class.